Welcome back, multivariable calculus friends. Hope everything's going well. I've changed things up a little bit, and I'm using an old worksheet that you might have seen in BC. I like this better than the notes packets that we've been using for reviewing, so we'll go with this one instead. And the main reason why I like it is that the notes packets that we typically would use only include the first 2 or 3 guidelines here for using integrals, and I'll kind of explain the rules and then we'll come back and do some examples. I posted this worksheet on as well as an answer key, so you've got plenty of practice to do. There's 14 problems. You can do this. I'm thinking what we'll be doing just to get a baseline grade for you every week, a daily grade, and then put in tests, is I'll put in a quiz probably Thursday or Friday. Only a few problems just to see if you've done anything. Shouldn't be all that hard, but something that you should be able to do. I'm sticking with multiple choice because, again, it is way too much to look at your work and grade. And I'm not certainly able to print out everybody's papers and do the full grade on them like I would if we were in classroom. Cutting corners here as well. So it is what it is. We'll keep going. The first chunk here, first 3, I guess, rules apply with integrals involving powers of sines and cosines. And I'll go through the rules and we'll kind of see these as we see examples. If the power of sine is odd and positive, we're going to save one of those sines, and it's a factor because we've got, let's say, well, for example, number 1, you can see cosine to the 3rd times sine to the 4th. Okay, so you're going to have multiple examples like that. So sine is odd and positive, save one of those signs and convert the rest of things to cosines. Okay, expand things out and integrate. So if you save one of your signs, you'll have a sine as an even power. Sine squared, oh yeah, Pythagorean identity. We should be able to think about that one. At the same time, if the power of cosine is odd and positive, save one of your cosine factors, convert everything else to sines. You might need to think about using the power reducing rule. So if the powers of both the sine and cosine are both even and non-negative, so not a fraction, make repeated use of the sine squared or the cosine squared. So we'll think about those, and then use guideline 2 as needed. There's also rules for secant and tangent. You can hopefully see why that would work, because the derivative of tangent is secant squared. The derivative of secant is secant x tangent x. So you've got those chances too. So the power of secant is even and positive, save out a secant squared, and convert everything else to tangents. If the power of tangent is odd and positive, save out a secant tangent factor. So a secant x tangent x, save out one of those. That way you'll have left an even number of tangents, and then you can convert those tangents to secants, again using the Pythagorean identities. If there's no secant factors and the power of tangent is even and odd, then you might have to convert a tangent squared factor to a secant squared factor, and then expand that out and integrate. And if nothing else works, I mean, this is the kind of harsh one, but if nothing else works, try converting to sines and cosines, and that's pretty harsh, but sometimes things will simplify that. All right, so let's do some examples. You've got, again, this worksheet, so and you've got the answers to these 14 problems. So do some of these and you should be fine. First one I want to do, in fact, is very similar to the first one that you have, except it's the opposite. So it's sine to the 3rd x, cosine to the 4th x, dx. Okay? So our strategy for this one is going to be to save one of the sine x factors. So it means I've got a sine squared times sine x. I'm going to save out one of the sine squareds. So I've got sine squared x times cosine to the 4th x times sine x dx. Why? Well, guess what? We're going to use u substitution. What do you think u should be? Cosine x. Why? Du is going to be negative sine. Ooh, I got to be careful those SIGN signs, don't I? Okay, so negative sine x dx. Good old song that we learned on Sesame Street back when I was a kid was one of these things is not like the other. And we've been encouraged to do something fun. So this is my something fun for the week. So share for your friends. I'll sing this song to you if you've never heard it. This was used to be on Sesame Street. Google it. It's this thing called the Google on the YouTube. You can look for it. It's a great song. Kathy, I think, was one of the ones that sang it. Big Bird sang it. One of these things is not like the other. One of these things just doesn't belong. Can you tell me which thing is not like the other by the time I finish this song? I'm pointing at the one that's not like the other. Now some of you are saying, OMG, they actually said that on Sesame Street. Yes, indeed they did. They did, because sine has no feelings. It's a way to discriminate against the sine here so we can get it to look like the other so we can actually solve the problem. It's called troubleshooting. Okay? So when you're out in the big, bad, scary world, maybe looking for what's different might help you solve a problem. Ooh, this part isn't working on my robot. Maybe I need to fix this part because it's not working. It's different than what the parts that are working. So think about that, you future problem solvers, you. I'm going to convert sine squared. The integral 1 minus cosine squared x times another cosine squared, x times sine x dx. Well, we've already said that that part is du. This is u, and this is u. In fact, let's go ahead and write the rest of our integral here. 1 minus u squared times u to the fourth times a du. The only thing I need is what? Don't I need a minus sign? I think I need a minus sign in here, don't I? Looks like I've made a mistake. So look for a minus sign because the derivative of u is cosine derivative. Yeah, u is, so I need a negative sign in here. So I'm going to squeeze in a negative sign. Okay, if I distribute all that, I should get the negative integral of u to the fourth minus u to the sixth du. U to the fourth. And I'm just distributing that u to the fourth, that one, that one, that one. Okay? So we've got that. So, well, I can use that to increase the power, divide by the power, increase the power, divide by the power. I'd get negative 1/5 u to the fifth plus, I'm just distributing that negative sign, 1/7 u to the seventh plus c. Negative 1/5. U, go back up there, cosine to the fifth x plus 1/7 cosine to the seventh x plus c. Okay, so what did you learn? Well, you learned that Sesame Street had a good message back then in the day, and you also learned that you can solve equations now that looked scary because whenever we had a product, we either had to do integration by parts, and that's one thing I will caution you. Once you've learned integration by parts, everything becomes a integration by parts. Well, I've got that part, that part. Those parts are the same type. So if you remember our ILATE or LEATE rule, that's not really going to help you. Okay, so sometimes you need other tools. I really like this unit because it helps us see if we're very good problem solvers. So you've got that one. Okay, so next one I want to do is the integral of cosine to the third x over square root of sine x dx. Well, that one looks different. That one definitely looks different. Okay, thinking about our rules here, I'm trying to save off something, aren't I? Trying to save off something. So if I said, and I've got an odd power of cosines this time, so if I save off one cosine, that's not my u, that's going to be my du. So what if I said u equals sine of x? Now don't worry about that square root yet. We'll get that in a second. But u equals sine of x, du is what? That's cosine of x. Okay? dx. So I'm going to split off one of those. And I write these out separately, so I would do that too. Cosine squared x, I'm saving that one because I'm not using that for my du, times a cosine x dx. That's going to be my du right there. I just underlined it, but right? That's part of my du over square root of sine x. Well, u is sine x, so I've committed to u being sine. Cosine squared's got to go. 1 minus sine squared over square root of sine x. And then I'll write one more time here, cosine x dx, but we know that's going to du real quick. Okay? In fact, I can't do u substitution anymore, but can I break this up as two fractions? As you can see, this unit is going to require us to use a lot of our skills, so that's okay. In fact, I'm going to go ahead and say u, because it'll be less writing. That's one thing I like, is one less thing to have to write with. That way you can focus on the math instead of the detail of what you're writing there. That's 1 over square root of u, or 1 over u to the 1/2 power, minus u squared over u to the 1/2 power. And that's all a du, and I should put parentheses around my whole integrand. Alrighty? Well, that's the integral of u to the negative 1/2 power minus what? Right? Because can't do 1 over u, and it's certainly not log of u to the, yuck, puke, vomit, wrong vomit. U to the what? Well, wouldn't that be u to the 3/2 power? And then we can use the power rule on each of those. Okay, so increase the power, divide by the power. U to the 1/2, divide by 1/2, that's 2. Minus increase the power, divide by the power. Well, if you're not seeing the new power, let's get that first. 3/2 plus 1 is 5/2. Divide by the power, flip and multiply. 2/5 plus c. Now you better not leave your answer like this, because that wouldn't be the correct, because you had a variable of x, not an integral of u. But you know that. So it'd be 2, and we could write this as sine of x to the 1/2 power, or rewrite that as the square root of that, minus 2/5 sine of x to the 5/2 power plus c. Okay. When I originally did this problem, I actually had limits of integration, so it wasn't an indefinite integral, but a definite integral. And don't worry, you probably won't see many of these that are like that. But if we had, we'd just, once you get your whole thing, then you'd use the fundamental theorem of calculus, apply in the upper limit minus the lower limit, and away you go. Okay? Alrighty, let's try another one. This next one I want to try, yeah, that'll work, is cosine to the 4th. Okay, so we've got an even power, so we can't really do that, can we? We can't split off one of the cosines, and we don't have a du anyway, so yeah, that won't work. But we do know this: cosine squared of x equals 1/2 plus cosine 2x over 2. Or you could put it as 1 plus cosine 2x all over 2. Either one's the same, right? So what we're going to do then is write the integral of this. Well, if I've got cosine to the 4th, doesn't that mean I have 2 cosine squared? So 1 plus cosine 2x all over 2 squared dx. Okay? If you want, you could factor out a 4, right? Because it's really 1/4. If I square that, that might make it easier just to not have to deal with all the fractions quite yet. 1 plus cosine 2x squared dx. Alrighty. So if you factored out that 1/4, right, because it's really 2 squared, so 1/4 comes out. Can I do u substitution now, because I've got an inside function? Yeah, but I don't have a sign for that, so that's not going to work. What else could I do? Maybe expand that, right? 1/4 integral 1 plus 2 cosine 2x's plus cosine 2x squared dx. I can take the antiderivative of 1. That's easy. I can take the antiderivative with a little work to make sure that I don't mess up the 2 there. So we could do that too. We got to square that, don't we? So I've got to use the power reducing rule again. Let's do that. 1/4 integral 1 plus 2 cosine 2x plus what? Well, it's going to be squared, so 1 plus cosine 4x over 2 squared. Now think about why it's cosine 4x, because this u here, if you're thinking u substitution, is 2x. So the angle that we're doubling is 2x, so now it's going to be 4x. Okay? And we'd have to expand that out, and this is still a dx. So let's make sure I don't make a mistake, because this is a good place to avoid trying to make a mistake, so don't do that. 1 plus 2 cosine 2x. Okay, that one's that. And I'm going to factor out a 1/4 like we did before, just to be safe. So 1 plus 2 cosine. Oh, you know what? We don't have a square. Yeah, this isn't squared, is it? So this is squared, this is not squared. So we're actually pretty good. Yeah, that was my mistake. See, I squared it like I did here because we had that squared. We only have one of these terms, so I've got the cosine squared. So that's the whole point. We're reducing the power. So we've got that. So cosine, let me strike this line. In an ideal world, when I get my YouTube channel, I'll edit that one out. But, you know, it's good to see mistakes because I make them. But it's good to catch them, too. So this is really 1/2, 1 over 2, plus cosine 4x over 2. Yeah, that'll work. That looks better. dx. Any questions? I'm going to combine that 1 and that 1/2 to be 3/2. Okay, 1/4, 3/2 plus 2 cosine 2x plus, it's really 1/2, isn't it? 1/2 cosine 4x dx. All right, time to take an antiderivative. This 1/4, we're going to save it. Isn't this 3/2 x? Okay, so we're going to distribute that in just a minute. So 3/2 x, that'll make us 3/8 x. Okay, plus, remember, you've got a du here, so this will be u equals 2x, du equals 2 dx. Well, look, you've got a 2 there, so that's kind of cool. So this is just going to be sine 2x. Okay, because we had the 2 already built in. Here, u equals 4x, du equals 4 dx. I need a 4 and I need a 1/4, right? So that'll be 1/8, won't it? 1/8 cosine 4x plus c. Distribute that 1/4, you get 3/8 x plus 1/4 sine of 2x. Okay, that sounds right. Plus 1/32 sine of 4x plus c. Plus c. And that one was, except for our little hiccup here, that one was not so bad. But shift that up there so everybody can see my work there. Any questions? Any questions? That was a good one. That was a challenging one. That was a challenging one. But you are up for the challenge. You can do this. Let's do one more. And since we've been doing sines and cosine examples, I wanted to at least do one example with secants in there too, secants and tangents. Secant to the 4th, 3x. Aha, so we're making it a little confusing now, another term there. Times the tangent of 3x, but we're going to have 3 of those too. So dx. Secant to the 4th, tangent to the 3rd. Secant to the 4th, tangent to the 3rd. Tangent's odd. Tangent's odd. And if we take the derivative of tangent, what do we get? A secant squared, okay. So we could save off a secant squared. That means we've got more secants, but we can convert those extra 2 secants into tangents, right? So let's try that. U equals tangent 3x. Du equals 3 secant squared 3x dx. Remember that 3 because of the chain rule. You got to know your derivatives of tangents. I mean, just this year I had a multivariable student ask, what's the derivative of tangent again? Yeah. Not happening. You got to know those, certainly. So I'm peeling off secant squared. I've got 4 of them. I need to save 2 of those for my du. So I'm going to peel off 2 of them. That means I got 2 left. Secant squared 3x, tangent to the third 3x, times secant squared 3x dx. Now, we need a 3 to finish our du, which means I need a 1/3. So I'm going to go u substitution now. Well, actually, am I ready to do u substitution? Not quite, right? Again, one of these things is not like the other. I'm trying to say u is tangent. So this is u to the third. This is du, all this right here. You got to go. Well, good news. We know what secant squared is. It's 1 plus tangent squared 3x times tangent to the third 3x times du. I'm already going to go ahead and substitute that du in there because I'm ready to write this out. Integral 1 plus u squared times u to the third du. 1/3 u to the third plus u to the fifth du. So substituting in and putting in the u powers makes it a lot easier to see and increase the power, divide by the power, etc. Okay? So we've got 1/3. I'll go ahead and distribute that in a sec when I replace my u's back with tangents. Isn't this 1/4 u to the fourth? Plus 1/6, I think, right? U to the sixth plus c, or 1/12. Tangent to the fourth, 3x, plus 1/18 tangent to the sixth, 3x plus c. All right? Any questions? Any questions? I'm hoping these are some good examples and you're getting back into doing some integration. Again, my goal, some of the multivariable calculus we did was really cool and all that. You're not getting credit for that, as we all know. But I want you ready to go, and this is part of me getting you ready to go. The more you take this seriously, the more you're going to be placing well on placement tests and doing a good start, being set for a good start at the colleges of your choice next year. So take care and do some homework. And what we're doing, if you've noticed, I've kind of spaced out the calendar a little bit because I'm just looking at things. It looks like what I'm going to do is have a lesson one day, practice the next day. Lesson one day, practice the next day. So I'm going to post them together in pairs in case you want to go ahead and we'll do it that way. Also, at the end of the week, either Thursday or Friday, maybe I'll make it available on Thursday and Friday, a real quick quiz just to see that we've done some homework for the week. Because I think the Big Bang Theory doesn't work for many of you. And since I'm spacing things out, I don't want to space out quizzes to one every other week. I mean, that's just not going to cut it either. So I'll do a quiz, and I will try. I'm thinking I'm going to be able to convert things into Canvas. So stay tuned. Hopefully you'll get a Canvas quiz on Thursday or Friday. I'm hoping everything's going well, and talk to you soon.